To all of you watching this video, thank you for watching and a very good afternoon. I am Mr. Ish. We're looking here at a very good integral, a definite integral which has a good learning merit to it because there's a lot you can learn from this specific integral. I want to present this integration process using two ways: the longer, slightly less efficient way, and then the shorter, quick, more efficient way, but both of those routes will have their own merits. We'll look at the longer, less efficient way first. When you're looking at that, you are thinking of a hyperbolic function. Let's start with the hyperbolic cosine, which has a graph like that, y-intercept of 0, 1. If this question were exactly what you're seeing, except you had a hyperbolic cosine, in that case you're looking at everything from minus infinity up to positive infinity. You're looking at all of this area, and you know you'd very likely have divergence come about, and you wouldn't have a good finite representation. But when you take the same hyperbolic cosine 0, 1, and now you do the reciprocal of it, you get the hyperbolic secant function, again from minus infinity up to positive infinity. There's no break, there's no vertical asymptote, there's no infinite discontinuity. It's just straight domain, minus infinity to infinity. You're looking at all of this area, and now you're probably thinking in your head there will be convergence. We'll have a good finite area representation, and you would be right. This right here is a type 1 improper integral, which will very likely display convergence, and you'll have a very good area here with regards to minus infinity to infinity and the area below the curve. It will be a very good one. Let's look at how we can examine this in the less efficient way, but it's still a good way because you learn a lot from that. When you look at this specific improper integral with the minus infinity and positive infinity, if you had these two limits, limit as x approaches minus infinity and limit as x approaches positive infinity, right over here and right here, for this function here, you would have a good answer, and in each case your answer would be 0 for both of these. Limit as x approaches minus infinity, your function approaches this horizontal asymptote, which is your x-axis, y equals 0. Limit as x approaches infinity, it approaches that horizontal asymptote, x-axis, y equals 0. So in both instances these limits are good. The corresponding limits of this improper integral are good, so you can evaluate very easily from minus infinity to infinity. You can do this the more longer formal way, and let's do it. You would do a limit as t approaches minus infinity. You would split your interval by bringing in a 0 right over here. You could do from minus infinity, which now is t, up to 0, and you have secant hx dx plus limit as t approaches positive infinity, you going from 0 up to t, which is positive infinity, secant hx dx. Remember, the longer way has its own merit. It's a good learning process. When you look at the antiderivative of hyperbolic secant, it's a very interesting one. It's inverse tan of sine hx. Inverse tan of hyperbolic sine. That's your antiderivative that you have from this function right over here, this hyperbolic. And then you're looking at it from 0 to t, and then of course you have this part, limit as t approaches infinity. You have again this inverse tan of hyperbolic sine, that's your function, and then you're going from a 0 up to t. Now the best way to put in these upper and lower limits, and the difference of the two is by means of a graph. You can do everything with a calculator. I'll do it with a graph. This right here is a graph of hyperbolic sine. It looks something like this. And this right here is a graph of inverse tangent x, and it looks something like this. You have a horizontal asymptote y equals pi over 2, then you have another horizontal asymptote y equals minus pi over 2, and your curve looks something like this. And in both instances of this right here, you have a good limit evaluation. Anyhow, you put the 0 in, you put the t in, you put the t in, you put the 0 in. Here the t represents minus infinity, here t represents positive infinity, and then you go from there. You'll evaluate with regards to hyperbolic sine. The output of that will serve as the input of your inverse tangent. When you're doing this limit, because the limits are good, the corresponding limits of this function are good, you can just very well evaluate everything. Hyperbolic sine of 0. When you're doing hyperbolic sine of 0, you're getting a 0, and that 0 goes into your inverse tangent, and you're doing inverse tangent of 0, and it's equal to 0. You're getting a 0 over here from the placement of 0. Then you know it's always a difference of the upper and the lower limit. Now let's do the t, the minus infinity. When you put minus infinity in terms of your hyperbolic sine, you're getting a minus infinity because it's going towards minus infinity. But when you put that output of minus infinity as your input of your inverse tangent here in this, you're looking here at this side of the curve. As your function is going towards minus infinity, it's approaching this horizontal asymptote of minus pi over 2, and that's what you get in terms of this evaluation. Remember, everything here you can do on a calculator. Now let's look at this part, the t and then the 0. Here the t represents infinity. When you put infinity in place of hyperbolic sign, it's approaching towards infinity. That's your output from right here. Then that output of infinity goes in your inverse tangent. Inverse tangent, as it reaches infinity, it approaches that horizontal asymptote of pi over 2, and that's your output from right here at the upper limit. The lower limit, you put 0 here, you're getting 0, hyperbolic sign of 0 is a 0, inverse tangent of 0 is a 0, and that's exactly what you're getting. A positive pi over 2, positive pi over 2, and you get pi. So this area which we are looking here at in terms of this area below the hyperbolic secant, utilizing this long, more formalized approach, is equal to pi, and that area is good. It's a good example of a convergence because this limit exists, and you have a finite area below this curve from minus infinity to infinity. There's no break, no infinite discontinuity, no asymptote, nothing. It's a nice, clean, smooth curve with a good area below it. Let's now look at the same function, but from the quick, easier approach. The quick, easier approach requires you to think of everything here, this same graph from minus infinity up to positive infinity in terms of even function, because you indeed have an even function here. From minus infinity up to positive infinity, you're really looking at something which looks like this. You have minus a and you have a positive a, you have an even function. That's exactly what you have, and dx. When you know you have that, you can do everything from 2 multiplied by 0 to a, your even function right here, and then dx. We have an even function here, and I'll show you why it is, because for an even function, f of x is equal to f of minus x. If you take the hyperbolic cosine, it has a definition of this e to the power of x plus e to the power of minus x over 2. If you do its reciprocal, right, the reciprocal which hyperbolic secant is, you get 2 over e to the x plus e to the minus x. This right here is your f of x. Now if you look at f of minus x, you're placing the minus x in places of those x's, and what do you get? You get 2 over e to the minus x plus e to the minus x. When you solve this out, you get 2 over e to the minus x plus e to the x. This e to the minus x, e to the x is the exact same thing as this. Order does not matter around a positive sign. So you have indeed proven hyperbolic secant is a even function, and you can utilize this property right here, and that's exactly what we will do. And we know it's a convergent function, the limits exist. Limit as x approaches minus infinity, your function will approach 0. Limit as x approaches infinity, your function will approach 0. These limits are good, corresponding limits are good. Your entire integral will be this now, 0 to infinity. We don't even need to apply the limits because we're showing you now the quick, efficient, shortcut procedure utilizing that, and we know we have limits which are good. We are looking at hyperbolic secant function dx. We know the antiderivative here is inverse tangent or arctan hyperbolic sine, and then we're looking at everything with a 2 at the very beginning because we are multiplied by 2, infinity and 0. We know based on the hyperbolic sine, and we know based on the inverse tangent, we have a curve which looks like this. When you're looking at the hyperbolic sine with infinity, your curve will go towards positive infinity. You feed the positive infinity here, your inverse tangent will go to pi over 2. It approaches pi over 2 in terms of the limit. From the upper limit you're getting of infinity, you're getting an answer of pi over 2. When you put the lower limit 0, hyperbolic sine of 0 is a 0, inverse tangent of 0 is a 0, and that's what you get. You get a 2 times pi over 2, right? And you know that's going to give you an area of pi, which we've already determined to be the case. For this area right here, area of this entire region below the curve from minus infinity to positive infinity is pi, and it's good. This right here is a quick shortcut procedure, or perhaps a more efficient procedure, because you're recognizing you have an even function and you can utilize this specific property. There's nothing wrong with you utilizing this property where something like this becomes this. Your only condition here is this. This value a and this value of minus a must be in the domain of that function for which you are utilizing. A positive infinity, minus infinity are within the domains of hyperbolic secant, because you very well see it here on the curve, and you can very well plug in those values into your function and you can arrive at a good limit value. Limit value here is always equal to 0, and here it's always equal to 0 with regards to minus and positive infinity. So these two values here, positive and minus infinity, are in the domain, so you can use this and you have an even function. So our integration procedure is completed for this. It's an excellent type 1 improper integral with this type of a setup in terms of intervals, for which you can use the longer procedure formalized approach or this shortcut even function approach. With regards to both options, your value is good pi, you have convergence, and you have a good area. Thank you for watching. Have a nice day.